Okay, so last day we had looked at aldehydes and ketones, at the nomenclature for aldehydes and ketones, and at their physical properties. What we want to look at now is the preparation of aldehydes and ketones. The good thing is that a lot of this stuff we've actually seen it before, and so this will just sort of corral those synthetic methods into sort of one segment. And so we can prepare aldehydes and ketones, one, by oxidation of alcohols. We saw this recently. For example, I can take a primary alcohol and I can oxidize it either with PCC in methylene chloride, because it has to be used methylene chloride, or I can use Swern oxidation. This is oxalate chloride, and that will convert the primary alcohol into the aldehyde. So, for example, I can take benzyl alcohol and treat it with PCC and methylene chloride, and that will generate benzaldehyde. And although aldehydes are further oxidizable, these reagents will not oxidize the aldehyde any further. On the other hand, I can take a secondary alcohol, I can treat it with the same reagents, and that's going to give me the ketone. For example, I can take 2-propanol and I can treat it with Swern reagent, and that's going to give me acetone. The difference is that, and so these are examples, the difference is that unlike aldehydes, which are further oxidizable, and therefore there is a danger that if your oxidant is too potent, it will oxidize the first formed aldehyde into the carboxylic acid. With ketones of course are not oxidizable. Ketones do not have either a carbonyl H or a carbonyl H. So I can certainly use these reagents to oxidize the secondary alcohol to the ketone, but I can also use Jones reagent, right, which of course is chromic acid, or I could use acidified permanganate. Because although they will oxidize an aldehyde to the carboxylic acid, they can't oxidize the ketone. Ketones are not oxidizable because they are devoid of both a carbonyl H and a carbonyl H. I'll remind you that for a compound in the oxygen series to be oxidizable, it must have one of these two substructures, either a carbonyl group, either an aldehydic H, right, an H attached to carbonyl carbon, right, a carbonyl H as it's often called, or a carbonyl H, an H attached to the carbon, the alpha carbon of an alcohol. And of course ketones, which have a carbonyl and 2 carbons, right, ketones have neither one of these substructures, and so they're not oxidizable. On the other hand, should I have used either Jones reagent or acidified permanganate to oxidize the primary alcohol, I'd have gone all the way, I'd have gone through the aldehyde into the carboxylic acid. But should I wish to stop at the aldehyde level, I've got to use one of these reagents. So I can still prepare aldehydes or ketones by oxidation of alcohols. I will also remind you that tertiary alcohols, being devoid of the carbonyl H and the carbonyl H, are not oxidizable, right? So these don't undergo oxidation. So the oxidation of a primary alcohol gives the aldehyde, but I've got to be careful in my choice of oxidant, right? They've got to be specific for alcohol to aldehyde only. I can oxidize a secondary alcohol to the ketone, and I can be much more, I can have a much broader choice of oxidants. The PCC and methylene chloride, the Swern reagent, or Jones reagent, or acidified permanganate. Okay? You notice we're not going to use Tollens reagent or Benedict solution because they have no action on alcohols. I can also prepare prepare aldehydes and ketones. This will be 2 by reduction of carboxylic acids. Although this is specific for for aldehydes. So if I take a carboxylic acid and I treat it with lithium, aluminum, tris-T-butoxyhydride, followed by water, I will generate the corresponding aldehyde. We pointed this out in class that this is a useful method of introducing a label. So if I had, for example, used lithium, aluminum, tris-T-butoxy-deuteride, followed by water, I would end up with RDO, right? I'd end up with, with RCDO. Right? I'd end up with a deuterated aldehyde instead. So I can prepare aldehydes by oxidation of primary alcohols or by reduction of carboxylic acids. I would not use LAH because that would reduce the carboxylic acid all the way down to the alcohol. Sodium borohydride has no action on carboxylic acids. When we get to esters and other carboxylic acid derivatives, there's some other reagents, other reductants that we look at, but for now we just keep it to these. I could also prepare these compounds by hydrolysis. So, for example, and we've seen this already, if I have, for example, a gem dichloro compound, right? Let's say I have, say, this compound. If I treat this with cold aqueous sodium hydroxide, I will do a hydrolysis of the carbon-chlorine bonds. And as we pointed out in class the other day, you can imagine that I replace both of these Cls by OHs to give a gem diol. Gem diols will spontaneously dehydrate to give rise to the carbonyl. And so my product of this reaction is going to be acetone. As I pointed out during class, that even though the gem diol idea is a useful way of looking at the reaction from a sort of a philosophical perspective, that is not, of course, how it happens. What you actually get is the hydroxide carrying out an SN2 reaction, and that generates this species, and you end up with a good leaving group, 2 bonds away from a source of electron density, and so you kick out the chloride, right? So you kick out chloride in both of these, and you end up with the conjugate acid of the carbonyl. And then the second hydroxide comes in, pulls off the proton, and you get your corresponding carbonyl compound. So you don't actually make the gem diol, but it's a useful way of looking at it from that perspective. Or you can say that since this compound is at the aldehyde level, we would make the corresponding aldo compound, the corresponding compound at the aldehyde level. So when I have haloalkanes, where the carbon is at the alcohol level, I can hydrolyze them under basic conditions to get the carbonyl compound. But we also know that we can have compounds that are basically ethers, right? Where we have a carbon attached to 2 OR groups. So these compounds are called acetals. We'll get to these in a little bit. I can hydrolyze acetals, but this time it's done under aqueous acidic conditions. And you could or could not warm it, really. It goes, you know, you can warm it. You don't have to heat it very high. What you'll get is the corresponding carbonyl compound and, of course, 2 alcohols. But I can use this as a method of preparing the corresponding carbonyl compound. So I can prepare carbonyl compounds by both by hydrolysis under basic conditions of haloalkanes. I can prepare them by hydrolysis under acidic conditions of acetals, which are just glorified ethers at the aldehyde level. And all of these we've actually seen before. We've seen all of these reactions before. Another way of making aldehydes and ketones is by hydration, right, of alkynes. And again, this is something we've seen as well. If I have, let's say, a terminal alkyne, I can carry out Markovnikov hydration using sulfuric acid and mercury 2+ as a catalyst. That's going to give Markovnikov hydration, so the H goes here and the OH goes there. That gives rise to the enol as the intermediate. But as you will recall, enols are one of those unstable classes of alcohols. They undergo a tautomerization. So it's called ketoenol tautomerization. And that gives rise to the corresponding ketone. I can take the same alkyne and carry out reactions to give an anti-Markovnikov reaction. And this is using diborane, followed by basic hydrogen peroxide. And that's going to give the anti-Markovnikov hydration. This is where the H goes here and the OH goes there. So we make this compound. And that, of course, is also an enol, but it's the isomeric enol, which will tautomerize. Right? It will tautomerize. This arrow is bothering me here. It will tautomerize to give rise to the corresponding carbonyl compound, which this time is the aldehyde. So I can prepare either the aldehyde or the ketone at will from the corresponding alkyne. I did point out, and again, this is something we've seen before in class as well. I did point out in class that this is also a way, if you look, I can ask you, how would I convert this aldehyde into that ketone? And what we've done is we've transferred functionality between adjacent carbons, right? And that suggests normally a carbon-carbon pi bond. If you're at the alcohol level, then it's an alkene, a single pi bond. If you're at the aldehyde level, then it's an alkyne. So what you would have done is you'd have converted this. So let me just do that. So this is kind of an aside. I would convert this compound into this one, right, using PCl3 at 0 degrees Celsius. Done an elimination to give rise to the corresponding alkyne. And then treat the alkyne with mercury 2 sulfate, essentially with sulfuric acid and mercury 2 plus to make the corresponding ketone under Markovnikov conditions. So this would be PCl3 at 0 degrees Celsius. This would be 3 equivalents of NH2 minus in mineral oil and heat, followed by water, and then this would be sulfuric acid and mercury 2 plus as a catalyst to do the Markovnikov hydration. And if I wanted to go this way with PCl3 again, to make the gem dichloro, then eliminate to make the alkyne, and then do anti-Markovnikov to make the aldehyde. And so, right, so we've looked then at 4 methods of converting, of preparing aldehydes and ketones. So oxidation of alcohols, reduction of carboxylic acids, and we see some more of these sort of reactions at the aldehyde level, at the acid level, when we get to those functional groups later on. There's hydrolysis, and then there's hydration of alkynes. Okay, so what we want to do now is look at reactions of aldehydes and ketones. And in order to do that, what we want to do is spend some time looking, as we did with alcohols, at what are the potential reactive sites in an aldehyde and a ketone of aldehydes and ketones. So I'm going to draw a generic aldehyde, and we're going to kind of examine what kind of chemistry we expect them to undergo. Well, it's got carbonyl O, and they have lone pairs of electrons. And by virtue of the lone pair, I'd expect it to be basic and nucleophilic. Okay. There is a pi bond, and pi bonds we know are relatively labile. And when compounds with pi bonds react, they tend to react by addition. So I'd expect them to see some addition chemistry. The carbonyl group, as we mentioned before, is actually a really good electrophile, right? And it's a good electrophile for a couple of reactions, a couple of reasons. One is that the sigma bond connects the more electronegative O to the carbon, and as a result, electrons drift from carbon to O, and so there's a dipole that's created. But juxtaposed with this is the fact that the carbonyl group is in resonance with a form in which there is a discrete positive charge on the carbonyl carbon and a negative charge on the carbonyl O. So you add these two things together, and what you actually find is the carbonyl group has a significant positive dipole, significant negative dipole on the O. So it's very attractive to a nucleophile. What makes it even better is that the carbonyl group, in order for chemistry to occur, the species has to attack the p orbital of the carbon, which means it attacks from either below or on top, which is great because it means they're approaching from a side that has minimal steric hindrance, because your substituents are going to be here. And certainly approaching from this side, that would be tricky, but that doesn't happen because there are no orbitals in this region. The region on the carbon where there are orbitals, and therefore where chemistry happens, is actually perpendicular to the molecular plane, and that is the direction that nucleophiles approach. So not only are carbonyl carbons great electrophiles because they are very positive looking, they've got huge dipoles, but because they're also sterically open. Okay? So I'd expect carbonyls to be nucleophilic basic by virtue of the electron pairs on the O, to be electrophilic by virtue of the high positive dipole on the carbon and the steric openness of attack on the carbonyl carbon. And I'd expect the pi bond to be cleaved and to get additional reaction. It also turns out that H's that are alpha to the carbonyl carbon are unusually acidic. And normally CH acids are very weak, right? For example, alkynes are very weak acids, and you need a strong base like amide to pull those protons off. But these are pulled off by mild bases like hydroxide. And it appears odd that we can deprotonate these species because you would think that the minus charge on the carbon, right, would make a stronger base than the minus charge on an O, because carbon is less electronegative, and as a result, this species should be far less comfortable. And you're absolutely right, except for the fact that this minus charge isn't really there, right? It's lost in resonance with the adjacent carbonyl group. So in fact, what you're looking at is a species that looks like this. And really, much of the negative charge, most of it in fact, is actually going to be on the O. So you can see why this reaction occurs, because now, whereas in the hydroxide, all of the minus charge is on the O, in this species, most of it is on the O, but a fair amount, right, is on the carbon. So you actually have delocalized the charge. You've actually delocalized the charge in this species. What you have is a scenario where most of the charge is on the more electronegative atom, but it's not as if the alpha carbon does not give you some assistance. So this actually is a weaker base than the hydroxide, which is why the reaction goes. If you look carefully though, this species looks like something we've met before, right? It really is, and it's the deprotonated form of an enol, right? This is an enol. So this species is referred to as an enolate. It's an enolate ion. The same way sulfuric acid gives sulfate, nitric acid gives nitrate. In the same way, enol, an acid, right? This H is acidic, right? It's attached to O, and if you pull it off, you get a resonance stabilized conjugate base. So this is an acid. Enol gives enolate. Now, we're going to do a lot of chemistry with enolates, but I will point out this at this point. Enolates are examples of what are called ambidont ions, because it literally has two teeth. It can attack from two sides, either the O, where the bulk of the charge resides, or the carbon, where there's still a significant amount of electron density. And it's interesting, it turns out that of the two sites of potential nucleophilicity, the one where you get the bulk of chemistry from is actually from the carbon, which makes a great deal of sense for two reasons. One, nucleophiles have to be willing to give up electron density. The O is more electronegative than carbon, and so O holds on to electron density much more effectively than carbon does. Carbon is not electronegative, it's uncomfortable with the electron density. So of the two sites, the one that is more desperate to give up the electron density is the carbon. So even though the O holds more of it, it's more comfortable with electron density than is the carbon. So it's a situation of having a strong person and a weak person, and you give the strong person 200 pounds to hold, and the weak person 50 pounds to hold. The strong person has no trouble holding 200 pounds. The weak person has great difficulty holding 50 pounds. And so the weak person is going to be one who's going to drop it, right? Because they're not comfortable holding onto that weight, even if it's a smaller amount. So most of the chemistry of enolates actually happens from the carbon. There's one exception we'll see later on with silicon, but ambivalent ions tend to do most of the chemistry from the carbon. So if I look at an aldehyde or a ketone, I expect to see what I'm going to call enolate chemistry via this H. And again, this is the carbonyl carbon, this is the alpha carbon, so this is called the alpha H. I'd expect carbonyl compounds to be acidic by virtue of the alpha H if they have one. And compounds having an alpha H are said to be enolizable, right? They're enolizable if they have an alpha H. This is called the aldehydic H. It's not the same as this one. And by the way, this is not acidic because if I were to pull this proton off, I think I have the diagram still. Yeah. If I were to pull this proton off, let's say there was an H. Let's say there was an H here. Well, that's not what I intended, but whatever. Let's say there's an H here. If I pull this proton off, right? If I take up this proton, I will be left with an orbital which is perpendicular, right, to the plane of this p orbital. So this p orbital cannot stabilize this negative charge by resonance. It can, however, stabilize this negative charge by resonance. So this H is acidic, this one is not. Okay? So the reactions I expect to see of aldehydes and ketones is nucleophilicity, basicity. They should undergo addition, and they should be attacked by nucleophiles because this side is electrophilic. So really, I expect to see nucleophilic addition to carbonyl compounds. Also, reactions not on the carbonyl group would include enolate chemistry at the alpha H. Let's take a minute, though, and compare the reactivity of aldehydes and ketones at the carbonyl group. So if I look at a carbonyl, and I look at a ketone versus an aldehyde, and I would ask, well, in fact, and so what I should do is look at specific examples, because that's a bit better. If I, for example, look at, let's say, look at acetone, and the isomeric propanol, so these are isomers, they've got exactly the same molecular masses, and I would feed them both. Let's say I started off with 1 molar acetone, 1 molar propanol, and I treat them with 1 molar cyanide. Okay. Now, there's not enough cyanide to go around for both reagents, right? So what would I get? It turns out that I would end up, now cyanide is a nucleophile, right? It will attack the carbonyl. If I have this as aqueous cyanide, it'll attack the carbonyl, right? The pi bond will break and I'll get an OH group on. So it turns out that what I'll end up getting is this species. So I'll have cyanide here. I'll also get this one. And I'll have, and I'm going to ignore stereochemistry for a minute. I'll have OH and I'll have CN. Right? There's an H understood here. But when I look at the relative yields, I'll probably get, and I'm just putting numbers of the sky number, but I'll probably get 0.75 molar of this one and 0.25 molar of this one. It probably won't be that huge a distinction, but let's just go with that for now. In other words, the aldehyde reacts faster with the cyanide than does the ketone. Okay? Aldehydes then are more reactive than the ketone. And the question is why? So, it's only fair to do this comparison if they are isomeric. It wouldn't be fair to compare molecules that have, widely differing masses, because now there's a question of, there's a question of rate of motion, and that affects the speed of reaction. That's not an issue here. These are isomers, so the masses are the same. And they're in the same solution, exposed in the same conditions. And yet the aldehyde forms more product. It reacts more rapidly. Right? Essentially, this is the hill that the aldehyde climbs. This is the hill that the ketone climbs. So I get more of the aldehydic product than I get of the ketonic product. So why is that? Well, it makes perfect sense, because remember we were saying that what attracts the cyanide to the carbonyl to begin with is the fact that the carbons of the carbonyl are quite positive. And obviously, the more positive it is, the more attraction there is, and in other words, the faster is the reaction. I look at the aldehyde, I've got a single alkyl group, and alkyl groups are electron releasing, dumping electrons onto the carbon. And let's say I then have a delta plus plus plus. Or in fact, let's do this. It's not quite a fair comparison, but if I look at the parent, the H's don't push electrons. So let's say I've got delta plus 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 on this carbon. On this one, I'll only have delta plus plus because the ethyl group, the alkyl group, dumps electron density and diminishes the positiveness, the positive dipole on this carbon. But here, I have two alkyl groups. And so the dipole on this carbon is only going to be delta plus. And ethyls and methyls and propyls and so on alkyl groups push to about the same extent. So it means the carbonyl carbon of a ketone is less electrophilic, it's less positive than the carbonyl carbon of an aldehyde. And so I'd expect aldehydes to be more reactive, more attractive to a nucleophile than would a ketone. So what we say then is ketones are electronically deactivated relative to aldehydes. But I can go one step further. Here I've got two alkyl groups, right? Flanking the carbonyl. Here I only have one. So it means then that when, I guess I erased it, that when a carbonyl group is being attacked by a nucleophile, again it's attacking from this way, if I only have one group, then there's a way, in terms of an aldehyde, my nucleophile can actually find a way to navigate so that it kind of hides away from this group somewhat. But if I have a ketone where there are two alkyl groups, then there's no approach to this carbonyl that can navigate around away from my alkyl group. So having two alkyl groups flanking the carbonyl sterically deactivates the carbonyl. So we say ketones are electronically deactivated and sterically deactivated relative to the isomeric aldehyde. So in general, aldehydes are more reactive than ketones. So we're going to break up then reactions of aldehydes and ketones into two types. We're going to look at reactions at the carbonyl carbon. Then we're going to look at what we're going to call enolate chemistry, which is chemistry at the alpha H, which involves deprotonation of the alpha H to make an enolate, a nucleophile, an ambivalent nucleophile, and then the subsequent chemistry of that enolate ion. So let's say reactions. Did I label that already or did I not? Yeah, reactions rather than ketones, good. So we're going to say reactions at the carbonyl group. Okay, so what do we expect? Well, the carbonyl group is planar. We have established that the carbonyl carbon is both electronically and sterically open, and that nucleophiles will have to attack either this way or that way, because that's where the orbitals are. So let's say cyanide. If I had cyanide as my nucleophile, it'll attack the carbonyl carbon, I'll break the pi bond. That will generate this species, right, which is the alkoxide. That will react with water, and that will generate the corresponding product. And it turns out this product belongs to a class of compounds called cyanohydrins. But that's the typical reaction, that nucleophiles will attack the carbonyl. The pi bond will break. We make an intermediate, which is tetrahedral. This is the classic tetrahedral intermediate. All right, and this is common at the aldehyde level when doing chemistry at the carbonyl group. That intermediate picks up a proton from water, which is either in the solvent or is added in the subsequent step, and I make my corresponding product. Overall, in this reaction, notice what we've done is we have added HCN across the carbonyl group. The H went here, and the CN went here. That's what we did. We added HCN across the carbonyl group. We kept the sigma bond intact. We broke the pi bond. So that's by definition an addition reaction. One of the points we had made earlier is that because the carbonyl group is planar, attack can occur from either the top or from the bottom. And if these two groups are the same, then there are no real consequences to that. If, on the other hand, the groups are different, then there is a consequence. So what we get is, and so let me get on a different page. What we can get is, if I have my carbonyl, and let's say it's acetaldehyde or ethanol, and this is attacked by cyanide, and it's attacked from the front, from the top. What I'll get is this species. I'll have CN, and cyanide and aqueous, right? We'll have CN, OH, methyl H. So in terms of priorities, this is first, this is second, that's third. So if I were to go this way, it looks S, but it really is the R compound because the H is in front. If I would attack from the bottom, I would have CN, OH, methyl in the back, H in front, and then CN. And this is clearly the S compound because you can tell these are mirror images of each other. So attack on the carbonyl that has two different groups, where I'm bringing in a different group. Because if I were bringing hydride, then I'd end up with a species that does not have a stereocenter. Right? I'd have two H's here. If I was bringing hydride, that would not give me R and S. Or if I was attacking with Me-, I'd have two methyls that would not give me R and S. It would not be optically active. It would not be chiral. But if I'm bringing a unique species on the carbonyl, I've got two different groups flanking it, and I'm bringing a nucleophile that is not either H- or Me-, I'm going to create a stereocenter, right? And if I have a single stereocenter, I'm going to be chiral. So I would say the carbonyl compound is pro-chiral, right? Really, what I should have said is pre-chiral, but that's not the term that's used. It's pro-chiral, meaning that just one reaction on this species, one nucleophilic attack, has the potential to give rise to a chiral site, a chiral molecule. But it goes better than that. I can distinguish the two faces of the carbonyl. Attack from the top face gives rise to the R enantiomer. So I'm going to call this the Re face of the carbonyl. Attack from the bottom face gives rise to the S enantiomer. So I'm going to call this the Psi face of the carbonyl. So the Re face is the one, when attacked by a given nucleophile, gives rise to the R compound. In this case, the top. The Psi face is that side of the carbonyl compound, that particular carbonyl compound, when reacted with a given nucleophile, yields the S compound. What is very important to appreciate, though, is Re and Psi are determined not by it's determined by more than just the carbonyl compound. It's a combination of both the carbonyl and the nucleophile. So, for example, if I take exactly the same carbonyl, and I'm hoping this works out because I haven't checked it before, but if I take exactly the same carbonyl, and I react it with, say, so this is methyl, H. If I react that with D minus, let's say I was using LAD, so lithium aluminum deuteride or sodium boron deuteride, it doesn't really matter. If I get attack from the top, right, so top, what I'll make is this compound. Right, so it's LAD followed by water. I'll make this compound. Right, so methyl H. This is first, second, third. Right, yeah. So first, second, third. I'm going this way, which looks R. This is actually the S compound. And similarly, if I attack from the bottom, what I would get would be this compound. D, OH, H, and methyl. This is clearly the R compound. So the top face here is the psi face. The bottom face is the Re face. Same face as in the top case, right? Same face, but different reagent. This is delivering D minus. So my point is, you can't just say that one face of a carbonyl is Re, because it depends on what the carbon is reacting with, right? So defining the face as Re or psi means looking at both the face of the carbonyl, the nucleophile, and the consequence of the attack. Does it give rise to the R compound or the S compound? So top attack by cyanide on this face gives the R compound. That is therefore defined as the Re face for that reaction. Top attack by deuteride on the same face gives rise to the S compound. That is therefore defined as the psi face for that reaction. So the face is defined as Re or psi more based upon the reaction, right, incorporating both the substrate and the nucleophile, than it is by the substrate alone. You can't do it in isolation. Okay, so attack of a carbonyl that is prochiral has the capacity to give rise to a chiral product. And again, it doesn't have to, because if I added hydride, I would get a species that is not chiral, right? And so prochirality may give compounds that are chiral, and further than that, I can identify faces that are either Re or psi, depending upon the particular reaction that's being carried out. So I'm just going to highlight now what are the kinds of reactions you see with carbonyl compounds, and then we're going to stop and look at it, do a different lecture. So these react with a variety of nucleophiles. They are, as I said, they're very potent electrophiles, and they can react with a number of species. So among the nucleophiles that they react with are R minus, right, followed by water. And this is in no particular order. And what they give rise to is the corresponding alcohol. They can react with H minus, right? So from, let's say, MH4 minus, this is either NaH or sodium borohydride, followed by water, typically. And that's going to give rise to the alcohol with the same number of carbons. And we've seen both of these reactions before. They can react with aqueous cyanide. They give rise to cyanohydrins. These are called cyanohydrins. Cyanohydrins themselves are interesting compounds. They can be hydrolyzed with aqueous acid. Nitriles are hydrolyzed. And what you generate is compounds that are called alpha hydroxy acids. Oh, that's a terrible diagram. No, that's just fantastic. These are called alpha hydroxy acids. They're used in alpha hydrox creams. Alpha hydroxy acids are biologically active. So lactic acid is an alpha hydroxy acid. A lot of the astringent creams that people put on their faces, women in particular, are alpha hydrox creams. So it's biologically active. You can also reduce these compounds with hydrogen gas and platinum, plus there are other specific reagents we're not going to get into. And what you end up with is you reduce the nitrile into the corresponding amino compound. So you get beta amino alcohols, right? So this is the alpha carbon, beta carbon, there's an amino group. So they're called beta amino alcohols. Carbonyl compounds can also react with alcohols in the presence of acid. I'm going to put H plus for now. And that gives rise to, we saw these earlier, these are acetals. They also react with ammonia and its derivatives. So I'm going to write ammonia and its derivatives as ZNH2. So ZNH2. And they give rise to compounds that have this formula. Let's see, so what have I left out? So R minus, H minus. Oh, obviously they react with hydrogen gas and catalysts, and you get the corresponding alcohol. We should have done it here, but whatever. You get the corresponding alcohol because you add H to the O and H to the carbon. Okay. And so we've actually already seen this chemistry, and this chemistry. And really this reaction as well, because I just looked at it a few minutes ago. But these two reactions of alcohols, those are of aldehydes and ketones. Those are new reactions, and this again is at the carbonyl carbon. And so we'll explore those in the next lecture. Okay, thank you.